Hi friends, in our last session we have completed with our chapter compressor. In today's session we are going to start with our new chapter, that is heat engine. This is Faizan Kagdi and I welcome you all to our lecture series of basic mechanical engineering. So let's begin. Today we are going to see first of all introduction to our chapter heat engine, and then we will study first cycle, that is Carnot cycle. Okay, so let's see introduction of this chapter. So first of all, defining what is heat engine. So we would say, so heat engine is a mechanical device which is going to convert chemical energy of fuel into heat energy. Yes, that is how. So we would say by combustion of that fuel, and that heat energy is further converted into mechanical power. Okay, that is rotational motion, and even we can call it as a shaft power. Now heat engine has four most important elements. That is, the first element name is heat source, second one is heat sink, third one working fluid, and last one is converting machine. So the first question comes, what is heat source? So we would say heat source is a large thermal reservoir which can supply infinite amount of heat energy. Yes, that is right. That is actually it's a hypothetical condition, but it can supply infinite heat energy without any change in its temperature. So do we have an example for heat source? Yes, that is sun. Right. Then heat sink. So heat sink is going to absorb heat energy. It is going to consume heat energy. Okay. So defining heat sink, so it is defined as a large thermal reservoir which can absorb infinite heat energy without any change in its temperature. So do we have an example for that? Yes, that is atmosphere. We know that hot gases are rejected in a surrounding atmosphere by vehicles, by automobiles, right? So it is basically absorbing heat energy of that hot gases. So we can say on a large scale that atmosphere is our heat sink. Similarly, next term is working fluid. So working fluid is a one which possesses heat energy, okay, which consists heat energy in it. Okay, so working fluid is going to supply its heat energy to a converting machine for converting its heat energy into mechanical power. So working fluid could be a product of combustion, that is hot gases, and in case of an external combustion engine it could be steam, right? That is steam possesses heat energy. Okay, and next one is converting machine. So as the name itself suggests that converting machine is going to convert heat energy of working fluid into mechanical power. Okay, so now with respect to these elements of heat engine, I have shown a flow diagram of a heat engine representing heat source, that is at a temperature TH, heat sink, that is at a lower temperature TC, and it represents that heat engine is going to generate work output, that is mechanical power, as we know, that is W amount. Okay, so I have given an example that let's say QS amount of heat is supplied by a heat source to a heat engine, out of which only certain portion is utilized and a remaining, that is QR, is rejected to the surrounding atmosphere. So how much is utilized? So we can say that W is equal to QS minus QR, that is utilized. Okay. We know that even from our Kelvin Planck statement that no engine can have a thermal efficiency of 100%. So 100% conversion of that QS into work output, that is W, is not possible. Okay, even we can understand this by taking an example that let's say QS is equal to 100 kilojoule which is supplied to a heat engine. Out of that, work output generated is 60 kilojoule, that is capital W, and a remaining 40 kilojoule is QR, which is rejected to our cold sink. Okay, so I hope guys that you are clear with our basic introduction of heat engine. Now let's begin with our first cycle, that is Carnot cycle. So giving an introduction regarding Carnot cycle, it was developed by Sadi Carnot in a year 1824. According to him, he has given a theorem that is called a Carnot theorem. No engine can be more efficient than a reversible cycle or a reversible engine which can operate between same temperature limit. Now let's see further. So there are certain assumptions which Carnot has taken for defining its cycle. The first assumption is working fluid that will be used to generate power is a perfect gas. But we know that perfect gas itself is a hypothetical assumption, right? That is, in actual case, Boyle's law, Charles' law and Gay-Lussac's law cannot be followed under all conditions of pressure and temperature. So perfect gas cannot exist, right? But assumption is that it is going to behave as a perfect gas. Next assumption is that wall of a cylinder and piston are considered as perfectly insulated, which means there will be no heat transfer between system and surrounding. That is, adiabatic process is taken into consideration. But we know that 100% insulation is not possible. That is, there will always be certain amount of heat transfer which can take place. Okay, third is compression and expansion process are considered to be reversible. Next assumption is that piston cylinder arrangement is weightless, which means there is no weight. It is weightless. Okay, next assumption, motion of a piston inside a cylinder is frictionless, which means there will be no resistance to the motion of a piston. It can move freely. That is, we can easily convert linear motion of a piston into rotational motion of a crank shaft. That is mechanical power. Now the process which are involved in Carnot cycle are as follows. So first process is considered as isothermal expansion is going to take place from state 1 to state 2. Then in the next process, adiabatic expansion process from state 2 to state 3. Next third process, isothermal compression will take place from state 3 to state 4, and finally adiabatic compression process from state 4 to state 1. That is, finally the system is going to return to its initial state in order to complete a cycle. Now the most important thing which we need to keep in mind is that he has considered two strokes. Remember this, two stroke. That is, in one stroke two processes are going to occur. That is, the first stroke name is an expansion stroke, second stroke name is a compression stroke, which means the first two processes which you can see on your screen, that is isothermal expansion and adiabatic expansion, will take place in one stroke, that is our expansion stroke, and in a second stroke, that is our compression stroke, remaining two processes, that is isothermal compression and adiabatic compression, will take place. So let's see how it's gonna work. We even need to draw pressure versus volume diagram for this topic. Okay, so on your screen, as you can see, I have represented a piston cylinder arrangement in which a first diagram represents isothermal expansion, then in a first stroke, and in the same first stroke further it is showing adiabatic expansion. Okay, then in the next diagram, that is third diagram, it is showing compression of a gas takes place, that is isothermal compression, that is our second stroke, and in the same second stroke further there is a adiabatic compression to bring our system to its initial state in order to complete a cycle. Okay, so remember that we are going to supply heat energy during isothermal expansion process. Similarly, heat rejection will take place from a system during isothermal compression process. So QS is the heat supplied during expansion and QR is the heat rejected during isothermal compression. So according to this, we are going to draw our PV diagram. Since he has considered that a working fluid is a perfect gas, so we know for a perfect gas isothermal process, the curve will be hyperbolic curve. That is from state 1 to state 2, as shown on your screen, and it is represented that QS is the heat energy supplied by an arrow. Okay, so from state 1 to state 2, it is isothermal expansion process, and it is also written that T1 is equal to T2, which means temperature at both the state 1 and state 2 is going to remain same. Okay, so because of that I have written T1 is equal to T2. Okay, now further, as we can see that expansion in the same stroke takes place but adiabatically, which means now the cylinder head is going to behave as an insulator, which means there is no heat transfer between system and surrounding. Remember that. So for the expansion, again we know that adiabatic expansion is represented by a hyperbolic curve. So from state 2 to state 3, you can see that hyperbolic curve is drawn, and further we are reaching at state 3. So we would say that first stroke has been completed. Okay, and at state 3 we would say there is a change in temperature, but how much? So T3 is a final temperature at state 3. Remember, at state 1 and state 2, since the process is isothermal, temperature is going to remain same, that is T1 is equal to T2. And in adiabatic expansion process, temperature has been decreased. Why? Because during an adiabatic process, expansion will take place at an expense of its internal energy. So the final temperature at the end of adiabatic process will be reduced. That is how much? So T3. Okay. Now, in a second stroke, we would say compression is going to take place to bring back the system to its initial state. Right. So from state 3 to state 4, it is representing a isothermal compression process. But during this process, temperature is going to remain constant, and at the same time, heat energy is going to be rejected to the surrounding atmosphere. So let's say that QR amount of heat energy has been rejected, and finally system has reached at point number 4, that is state 4. And from state 4 to state 1, that is finally adiabatic compression is taking place to bring a system to its initial state 1. So over here, remember that at state 3 temperature is T3, at state 4 temperature is T4. But since it is isothermal process, so temperature is going to remain same, constant. Okay, so T3 is equal to T4. Remember these two conditions. Now we are going to derive efficiency for this Carnot cycle. Okay. Now, if you remember that for efficiency formula, it is output upon input. Okay. Now, what is an output in case of our heat engine? So, as we have seen our flow diagram, so output is our work output, capital W. And what is the input? So, we would say input is QS, that is heat supplied. Remember the flow diagram, that is we were supplying QS amount of heat energy, and QR was rejected to the surrounding atmosphere, and W was a work output. So we would say that efficiency is output, which is capital W, upon input, that is QS. So our target over here will be to determine capital W and QS. So first of all, let's determine how much is the heat supplied. So QS is equal to P1 V1 ln or log V2 by V1 to the base E. So this equation we have actually obtained during our chapter properties of gas. If you remember, we have determined 5 terms. Okay. So one of the terms is heat transfer during this isothermal process. Okay. Now further, I have substituted by using characteristic gas equation, that is Pv is equal to mRT. Now considering mass equals to 1 kg, so we can write equation is equal to RT1 log V2 by V1 to the base E. Now let's say that V2 by V1 is represented by small r. Okay. So I have placed over here RT1 log R to the base E. Now in the next step, let's determine how much is the heat rejected during this process. So heat rejected is denoted by QR. So QR, again we would say it is rejected during isothermal compression process, right? So we are going to apply our same formula, that is P3 V3. Now it is from state 3 to state 4, right? Compression process is from state 3 to state 4. So we have written P3 V3 log V4 by V3. Okay, further we can write P3 V3 as mRT3, right? So M is 1 kg, so RT3 log V4 by V3. Now we are going to use result of our two process, that is a adiabatic expansion process from state 2 to state 3 and adiabatic compression process, that is from state 4 to state 1. By using a TV relation, temperature and volume relation, we were getting that V2 by V1 is equal to V4 by V3. So in the next step, I have directly placed small r, that is V4 by V3 is equal to small r. So this is our equation for heat rejected. Now let us determine work done during this cycle. So we know the formula of work done, W is equal to Qs minus Qr. Now RT1 log R to the base E minus RT3 log R to the base E. Okay. Further, I have determined thermal efficiency, that is eta is equal to, as we know, output upon input. So W upon Qs. So I have directly written Qs minus Qr by Qs. Cancelling Qs from numerator and denominator, we can directly write 1 minus Qr by Qs. Okay. Now in this step, I have substituted value of Qr and Qs. So as you can see on your screen, I have written 1 minus in a bracket RT3 log R to the base E upon RT1 log R to the base E. Okay, so from this you can clearly see that R log r to the base e will get cancelled out. So the final equation is going to become 1 minus T3 by T1. So this is our final equation of efficiency for Carnot cycle. Okay, now let's see what are the limitations of this cycle. So it is very obvious that whatever are the assumptions will be considered as the limitations of this cycle. Now the first limitation, it is very obvious that Carnot cycle is hypothetical, that is totally based on assumption, imaginary concept. Okay. Next is that thermal efficiency of this Carnot cycle is dependent on a temperature of source and temperature of sink. It does not depend on which type of working fluid we are using, right? So as we have seen, the formula was eta is equal to 1 minus T3 by T1, which was just depending on a temperature of heat source and heat sink. Okay, higher temperature and lower temperature, which means irrespective of working fluid, whatever you use a working fluid, it is not going to change the efficiency of a cycle, which is a limitation. In actual case, it is not possible. If we use a petrol or a diesel, so the efficiency of an engine is definitely going to change, right? Now, third one is, practically it is not possible to neglect friction between piston and cylinder, which means there is obviously some amount of friction between piston and cylinder. We can reduce friction, but we cannot eliminate friction. We can reduce friction by making use of an engine oil, that is lubricating oil. Okay. Fourth one, in one stroke, as we know that two process takes place, that is isothermal process and adiabatic process. But for isothermal process, piston has to move at a much slower rate, right? That is, it is required that system should get a time to transfer heat energy from a system to a surrounding in order to achieve constant temperature at a final state. Whereas for adiabatic process to take place, piston has to move at a much faster rate, which is practically not possible to take place in a single stroke. That is, first moving slowly and then suddenly moving at a faster rate, which is not possible, right? Now, in the last point, the output octane per cycle is very small. Okay, so guys, I hope that you are clear with the introduction of this chapter and Carnot cycle. In today's session, we are keeping up till here. In our next session, we will start with our topic Rankine cycle and Otto cycle. So till then, stay tuned and thank you all.